Okay, hello everyone, and welcome to the presentation of this paper. And the title of this paper is Intelligent Contingency Overload Avoiding Control of Battery Energy Storage for Renewable-Rich Local Area. And the authors of this paper are Viktor Astapov from Tallinn University of Technology, Estonia, Kosu Abdellah from the University of Delft, Franklin Olivo from F. Olivo Power Consultancy, Jose Luis Reda and Professor Peter Palensky from Delft University of Technology, and finally Harold Chamorro from KTH Royal Institute of Technology, Sweden. And let's start with this presentation. As you must be aware, the modern world is pushing really hard for the integration of more and more renewable. And the idea of this renewable energy is to cope with the climate change. However, one of the main issues of this renewable energy is that they are weather-dependent power production resource. As a consequence, as we integrate more and more renewable energy resources, well, the curtailment of this weather-dependent generation is increasingly creating a concern for the transmission system operator. In particular, PV system and wind power plants, they create a massive concern for the transmission system operator in order to ensure the stability and the reliability of the electrical power system. And also, there are some very important losses, economical losses related with the energy, and also the economic impact related with the power purchase agreement. As a consequence, well, the problem starts to be very, very important for the system operator, and even more important when we are talking about contingency situations. In this paper, we are looking to use a battery energy storage as a solution to deal with the very important issue of the overloading of the transmission system, where we are connecting in a very rich PV generation area. For that reason, this paper is proposing a battery energy storage control that targets to reduce the transmission line overloading by intentionally charging or discharging the battery energy storage in order to deload the transmission system at the time that the PV production is extremely high, and we don't want to curtail that kind of generation. But let's start with the proposed control. In order to demonstrate, in order to show you the proposed control, let's consider this very simple power system. In this power system, we assume that on the left-hand side, we have external power system that is huge. There are two transformers, there are transmission lines in parallel, line 1 and line 2. Then we have a rich area, PV rich area, that is located on the right-hand side and connected to bus bar number 3. Now, as you can see, the local area on the right-hand side is very rich in renewable, in this case in photovoltaic power plants. But now, what's happened if we have a single contingency at the transmission lines? Let's say that now we have a fault at the transmission line number 2, and suddenly there is a disconnection. Well, as you can see, between bus bar number 2 and number 3, we stay working with a single transmission line, and the total active power moving through that transmission line will be basically the difference between the power demand, the local power demand inside the local PV rich area, and of course, time dependent on the power production, active power production of the PV power plant. However, what is important here is that you realize that depending of the power balance between the demand, the local demand, and the local generation, there is a possibility that this transmission line become overload. And for that reason, we are proposing the use of battery energy storage in order to reduce this overloading condition. And here, what I am presenting is that we are connecting a battery energy storage here at the bus bar number 3 at the same common connection point of the power plant, the PV power plant, in order to minimize the overload on this transmission line. And what we are proposing is a very interesting and a very simple control. In this case, we have the battery energy storage connected here. Of course, we are proposing an intelligent overload avoiding control, and this intelligent overload control requires to sense or to know the state of charge of the battery. Because in order to provide or to deliver the service to the transmission system, we need to have enough capacity, enough room in order to manage the battery charging or discharging the battery. On the other hand, this controller, this intelligent overload avoiding control, is creating the reference for this converter installed at the battery energy storage. And to do so, we are collecting information about the active power that is balancing here in this bus bar, okay? What I will do now is I will jump into very specific details of one example. Let's start with a case where we have a demand that is basically having two components. One component is a commercial demand, as you can see here in green color, where the peak load is happening at 8 in the morning. And also we have here a residential load, and this residential load is huge, and you can see that the peak load is reaching around 6 p.m. and with a peak demand of 46 megawatts. However, this is the condition that we call base case. We don't have any PV generation. Because when we have the PV generation, there are two possible cases. There is a case where we have a very small PV power plant. If we have a very small PV power plant, you can see here in orange color, we have a very small proportion of active power generation. You can see that is reaching around 17 megawatts around 1 p.m. However, if we increase the penetration, I mean the power plant that is installed over there is huge, you can see here how the power production during the sunlight hours is overcoming and reaching almost 70 megawatts at 1 p.m. But now, what is important that you realize for scenario 1, low penetration of PV, and scenario 2, rich PV area, what you can notice is that here we have the classical dot curve. You can see here how during the sunlight hour, the apparent load from the transmission system is reduced. In fact, scenario number 2 is quite interesting because there is a reverse on the power flow on the transmission line. But now let's examine what is the situation when we start to look into the loading of the transmission line. Well, scenario 1, if we have some PV generation that is a low penetration, well, you can see here how the small power plant is allowing to reduce the loading of the transmission line. You can see here how the loading is below 20% around 2 p.m. when you compare with the base case that was around 50%. However, when we have the PV rich area, I mean we have a huge power plant connected to the bus bar number 3, the situation starts to be quite interesting, because this change on the direction of the power flow at the transmission system create a very interesting situation. As you can see here, around 8 a.m., the PV power production starts to increase and pick up, and you can see how the loading of the transmission line is decreasing. Then, when we have enough PV power generation, you can see how the reverse of the power flow at the transmission line increase the loading of the transmission line here. And that is quite interesting. Now, what I will do is I would like to know the effect of having a single contingency. In this case, we are tripping the transmission line number 2 and looking into the loading of the transmission line number 1. And what is the situation here? Even for scenario 1 or scenario 2, as you can see, there are several hours where the loading of the transmission line is above the maximum loading allowed, that is 100% for this very specific case. Now, what we want to do is basically use the battery energy storage to solve this problem. And what we are doing is something very interesting. We are allowing the battery to charge during the sunlight hours, reducing the power that is exported from the PV rich area. But this power will be later used for 2 different conditions. That condition, during the night hour, that power can be sold to the local customers, reducing the loading of the transmission line during the night. But at the same time, during a contingency, I have room to charge the battery, and as a consequence, I can reduce the overloading. For instance, here on the right-hand side, you can see that the contingency is happening at 1 p.m. As you can see, suddenly there is an increase of the loading, but at the same moment, the battery energy storage is charging. As a consequence, this very specific charging has been optimized to reduce the overloading on the transmission line. And in this condition, that before we install the intelligent battery energy storage system, well, in the previous condition was overload. Right now, the loading is below 100%. But now let me do it in another moment. Now let's assume that we have the contingency at 7 p.m. At 7 p.m. we don't have sunlight, or the sunlight production is very small, and in that case we can take the advantages of discharging the battery in order to produce local power, minimizing the overloading of the transmission line. As a consequence, in this paper, we implemented, we designed, we implemented, and we tested a very specific controller designed to avoid the overload of the transmission line when we have a contingency. And this is the preliminary step on defining a better control for battery energy storage that can offer several services in normal condition and in emergency condition, and try to show you that there is no need for curtailment PV systems when we have enough capacity and an intelligent controller to avoid this kind of situation. Here there are some references, and now we are open for questions. Thank you very much for watching the video, and we are here for answering your questions. Thank you.